We're ready to go.
Good afternoon, everyone, and thank you for joining our presentation on temperature and humidity control in your LI-6400 XT leaf gas exchange system. Light carbon dioxide, temperature, and humidity are among the environmental variables which influence plant gas exchange rates. In this presentation, we're going to talk about temperature and humidity control, but it's important to remember that all the variables are linked. Light causes stomates to open, which increases leaf chamber humidity, but it also causes more CO2 to diffuse into the leaf and be assimilated, which reduces the chamber CO2 concentration. The absorption of radiant energy increases leaf temperature, opening of stomates increases evaporation rates, and that can cool the leaf. Similarly, stomates respond to changes in CO2 concentration, which can in turn lead to changes in chamber humidity. First, we're going to discuss temperature. Just as you have a temperature preference, which may be the same or very different from others in your life and in your office or lab, causing fights over the temperature controls, plants also have a temperature preference. A change in temperature can affect many things, large and small, everything from protein balance and enzyme kinetics to membrane fluidity to vapor pressure deficits. Monitoring the temperature of a plant and keeping it within the optimal range for your individual species can help ensure that photosynthetic measurements aren't affected by temperature, and thus the variable you want to look at is not confounded by the variable you didn't want to look at. As an example of why temperature is important to understand and to monitor, think about the peanut. It is yummy. It's also an important agricultural crop, and it has very distinct preferences about temperature and water stress. If temperature is too high, the yield decreases. If temperature is too low, the yield decreases. So a biotic irrigation model for precision agriculture was based on temperature optimums to tell farmers when they might need to add extra water and decrease the temperature stress and vapor pressure deficit for their crop. If they hadn't focused on temperature, they wouldn't know, hey, I need to water these plants. They're a little bit stressed out by the heat. Another example of temperature's importance is invasive species research. On the left is a picture of carex, which is a native grass. On the right is phalaris, which is an invasive grass. By studying the gas exchange properties of these two species, researchers were able to understand that the invasive grass, phalaris, had a wider range at which it was photosynthetically active, which increased its opportunities for carbon fixation and thus increased its growth patterns and its ability to move in on the territory of the native grass. Next, Tan's going to talk about humidity control and a little experiment to show you why humidity is important now that we've talked about temperature.
Thanks, Elizabeth. While Tanveer takes his place, I'd like to remind our audience that they can join the Twitter conversation by using the tag #6400XT. Tanveer?
Thanks, Ashley. This slide here is a stylized or a cartoon illustration of the boundary layer, and is definitely not to scale. This is just to explain the boundary layer. Within the boundary layer, there is no turbulence. The movement of molecules is by diffusion, and that takes place in response to mole fraction gradients. The diagram on the left depicts an expanded boundary layer, whereas the diagram on the right depicts a much thinner, contracted boundary layer. The thickness of the boundary layer depends on the wind speed and leaf dimensions. Stomates respond primarily to the humidity right next to them, i.e. the humidity within the boundary layer, not the general or ambient humidity a few centimeters away. In a few moments, we will see an actual response of a rice plant, rice leaf, to the adjustments of its boundary layer thickness. For a little more realistic appreciation of the boundary layer thickness, consider this diagram and equation. It can be shown that the boundary layer thickness, delta in millimeters, is a function of the wind speed, u in meters per second, and the distance across the leaf in meters. As an example, a 10 centimeter wide leaf exposed to a breeze of say 4 meters per second would have a boundary layer thickness of just over 0.5 millimeter. This slide illustrates how The leaf chamber mixing fan of the LI-6400 vigorously circulates air over both sides of the leaf. Inside the LI-6400, the wind speed is much higher than typical field conditions. If you open the LI-6400 leaf chamber when it is running and listen, you will know what I mean. Under field conditions or in greenhouses, the stomates are not exposed to such high wind speeds. The higher wind speeds inside the LI-6400 leaf chamber are employed to ensure that boundary layer resistance is a small part of the total leaf resistance to the movement of water, so that stomatal conductance measurements are not subject to uncertainties in the boundary layer conductance estimates. Conductance is just the inverse of resistance, and we seem to use them interchangeably. Typically, the two-sided boundary layer conductance of the LI-6400 leaf chamber is of the order of about 3 moles per square meter per second, whereas the typical two-sided stomatal conductance of a leaf might be in the range of 0.01 to 1 mole per square meter per second, depending on stomatal conductance and the number of stomates. This slide shows a leaf of a rice plant clamped into the LI-6400 leaf chamber. Rice is a species whose stomates are often sensitive to disturbances caused by clamping into leaf chambers. We used this rice plant grown in our greenhouse and a sequence of display snapshots from the LI-6400 to illustrate the importance of controlling chamber humidity when taking leaf gas exchange measurements. Here are 2 LI-6400 display snapshots while taking measurements on the rice plant shown previously. The light level was set to a constant value of 1000 micromoles of photons per square meter per second before the leaf was clamped into the sample chamber. The desiccant control knob was set to full bypass. The photosynthetic rate and stomatal conductances increased gradually from near zero at the beginning to over 8 micromoles of CO2 being assimilated per square meter per second, and about a stomatal conductance of about 0.1 mole per square meter per second. After about 20 minutes, the reference and the sample gas analyzers were matched to eliminate errors due to analyzer offsets. The discontinuities that you can see in this strip chart on the top are when the gas analyzer was matched. After allowing the leaf to acclimate for a further 15 minutes or so, the gas analyzers were again matched, and then the desiccant knob was put to the middle, so that just about 50% or maybe a little bit less of the air was scrubbed and the remainder bypassed the desiccant. Notice the decrease in the reference and sample chamber water vapor mole fractions from about 20 millimoles per mole shown previously down to about the 14 millimoles per mole shown here. Actually, the range is around 13 to nearly 16. The sample chamber relative humidity has also decreased from nearly 66% shown previously down to 48% shown here. The air temperature was about 25 degrees Celsius in both cases. The sample chamber airflow rate, the light, and temperature were left unchanged. Although in this example we have used the desiccant control knob setting to modify sample chamber humidity, in general changing the airflow rate has a bigger effect on sample chamber humidity. Elizabeth will explain this in more detail later in the presentation. Within about 5 minutes of changing the setting of the desiccant control knob to the middle position, the stomates began to close. This was in response to the reduced humidity, and net photosynthesis also decreased, as can be seen here. Also notice in the lower left-hand side of the upper display snapshot that the leaf fan is set to fast. The stomatal conductance and net photosynthesis continued to decrease for this test leaf over the next 10 minutes. We then reduced the leaf chamber mixing fan speed from the fast setting, which is a 5-volt setting shown previously, down to a value of 3 volts, shown here above the function key F1 in the upper display snapshot. The point at which the mixing fan speed was reduced was marked by an arrow in the strip chart using the mark function that you can see in the lower display. The incoming and sample chamber humidities are virtually the same as in the previous slide, but the stomatal closure was arrested just by reducing the wind speed around the leaf. Reducing the fan speed increases the boundary layer thickness. The leaves of rice plants are often quite sensitive to small changes in humidity within the boundary layer. Greenhouse-grown plants where wind speeds are low and stressed Mediterranean species often show similar sensitivity to small changes within their boundary layer due to changes in the wind speed and ambient humidity. If you clamp onto a leaf with your LI-6400 and notice stomatal closure, such as shown in this screenshot, then that's a sure indicator that you need to increase humidity and or decrease the leaf chamber mixing fan speed. With care, even the most sensitive plant species can be dealt with the 6400. Just prior to capturing these display shots, the desiccant control knob was set back to the full bypass position, and the sample and reference gas analyzers were matched again. Notice that the sample and reference chamber water vapor mole fractions are back to the original values of around 20 millimoles per mole, and the sample chamber relative humidity is back up over 62%. The mixing fan voltage was left at 3 volts. With the higher chamber humidity and the reduced mixing fan speed, you can see that the leaf has begun to recover again. And from these two strip charts, they're both taken one after the other. Stomates tend to close down faster than they will reopen. So watch out for the response of leaves to being clamped into the chamber, and be ready to take quick action, because they will close up and they'll take a long time to reopen. After a few trials, most people can learn to take gas exchange measurements with the LI-6400 even on very sensitive leaves. A good way to start is to set the chamber humidity a little bit above the ambient, say 5% above ambient. The idea being that keeping it higher than the ambient humidity inside the leaf chamber can compensate for the compressed boundary layer. The higher wind speeds inside the leaf chamber are, of course, employed to ensure that uncertainties in the boundary layer resistance have little or no effect on the estimation of the stomatal conductance. With time, in this little experiment, with time, when the leaf continued its upward trend, and stomates began to open and photosynthetic rate continued to increase after putting the leaf in a more comfortable situation. And after about 30 minutes from going back to the original, more comfortable chamber humidity setting, the leaf was almost back to where it was previously. Notice that in this display, the transpiration rate is 0.99 millimoles per square meter per second. The desiccant control knob was again momentarily in this situation, in this display here, was set back to the full bypass, from the full bypass to the partial scrub. Notice that sample chamber relative humidity has dropped from the 65% value shown previously to a value of 47%. The leaf saturation deficit is also shown here and has a value of about 1.7 kilopascals. With time, no doubt, the leaf would again respond by closing down the stomates to this more drier condition. But notice that even with an almost identical stomatal conductance of 0.08 moles per square meter per second, leaf transpiration rate in this case is significantly increased, and it is 1.57 millimoles per square meter per second, whereas previously it was 0.99 millimoles per square meter per second, even though everything else is the same. And what this illustrates the point that whereas stomatal conductance is an intrinsic property of the leaf, leaf transpiration rate is a function of chamber conditions and might be quite different from field conditions. Leaf transpiration rate is not a particularly useful parameter to report, as it can be easily manipulated. Its main value is that it is used to determine the leaf intrinsic properties such as stomatal conductance and CI. So please, no more comparisons of transpiration rates of leaves in chamber measurements. They are really not that important. They just need to calculate the intrinsic property of stomatal conductance and CI. Okay, here's a recap of the points that we covered. Some plants such as rice, greenhouse-grown plants, and stressed Mediterranean species can be very sensitive to chamber humidity and leaf chamber fan speeds. So watch for stomatal closure when clamping onto leaves. Take action quickly because stomatal closure can occur very quickly, often in less than 5 minutes, whereas stomates reopening can take 20-30 minutes or more. Start by using a leaf chamber humidity that is a little bit above ambient to compensate for the compressed boundary layer because of the higher wind speeds employed. And if necessary, increase leaf chamber humidity and reduce chamber mixing fan speed to increase the boundary layer thickness. I think we have a poll question coming up next.
Thank you, Tanvir. The poll question should be up on the screen, and it is, are you concerned about controlling temperature, relative humidity, or both? To answer, just click the radio button next to your response, and we'll give everyone just a few minutes to choose an answer.
Well, it looks like we have an interesting mix of people who are interested in controlling temperature, relative humidity, and both. So first, we're going to talk about controlling relative humidity. I really appreciate Tanvir explaining the theory of humidity control, so now we're going to talk about some practical elements. The most obvious place to control relative humidity, as you saw in Tanvir's experiment, is the scrub bypass knob on the desiccant column. You know, you can scrub out all water, or you can use all the available water in the airstream, whatever you happen to have. In general, you want to start with the knob in that loose sweet spot in the middle, so you have a maximum range of adjustment in both directions, but there are exceptions, as Tanvir's experiment noted. One non-exception is that unless you're zeroing the gas analyzer, you never want to have the knob turned to full scrub, because you've just put your poor plant into a desert, and it is not going to be happy about that. However, in many cases, as Tanvir also mentioned, changing the flow rate is more efficient than just changing the scrub setting to bypass. You can kind of think of this as two different levels of a microscope. The coarse adjustment is just changing the scrub bypass knob, but when you really want to get an idea of what's going on and really control things pretty well, you can also change the flow rate. That's the fine adjustment. So as you can see from the graph here, the difference between partial scrub and full bypass, if you also combine it with changing the flow rate, you can get a much larger in-chamber humidity level range. And if you're in a situation where you really are having issues keeping your plant in that happy spot of 50 to 80% RH sample, you might want to consider changing the flow rate. It's going to slow your measurement slightly since it takes longer to flush the chamber when you slow the flow rate, but good humidity levels are maybe worth a slightly slower measuring process, especially if you're in really arid measurement environments. So the next thing you can do if changing the flow rate and changing the scrub bypass knob isn't getting you where you need is you can moisten your soda lime. This is something you can do while the instrument is on, although obviously you shouldn't take measurements at this point. So you're going to take the soda lime tube off the instrument, you're going to open it up, you're going to use a lab squirt bottle to add 10 mils of DI or lab type water, not tap water. There's interesting things in that sometimes, but not nanopure water either, because you don't need to find the microbiology labs. And you're going to add 10 mils of that water to your soda lime tube and then close the chemical tube. Remember to tap the cap on the threads to get rid of any soda lime dust that might be causing leaks. And then shake the tube to prevent the soda lime from clumping at the top. Put the tube back on the console and keep going. You'll have added humidity to your airstream and regenerated your soda lime, so it's a win-win situation.
Elizabeth, can I interrupt with a question?
Sure, I'd love to take a question.
How often can soda lime be reused, and what happens when it can't be used anymore?
Oh, that's a good question. Typically, soda lime can be reused multiple times. We've got some customers who've told me that they've been reusing and regenerating their soda lime for about a year now. I think that's the maximum people have used it. But towards the end, you may notice that it's turning violet or it's getting a little bit crumbly or even regenerating isn't doing it. And at that point, it's time to switch out your soda lime. When it can't be reused, you may need to talk to your institution's environmental health and safety officers. Some places require hazardous disposal of soda lime. Others just allow you to throw it in the trash. So you need to make sure that you find out what your institution wants you to use and make sure you don't accidentally put hazardous waste in the trash.
Thanks, Elizabeth.
Yeah, thanks, Ashley. That was a great question. Now we're going to talk about controlling temperature, because we talked about why we want to control humidity and why we want to control temperature. So now we're going to talk about some more concrete stuff. The first thing is that it's important to understand the difference between leaf temperature and block temperature before you decide which one you want to control, because the LI-6400 will give you an option to control either. Leaf temperature thermocouple is a fine wire thermocouple. As you can see in the slide, you've got the thermocouple assembly in the leaf chamber. The block temperature is within the body of the sensor head. And so, that's a little bit more precise. It's easier to control the block temperature and have it transfer to leaf temperature than to try to control the leaf temperature itself. Because what you'll essentially be doing is, if you ask it to control leaf temperature, you are controlling block, and then it's just trying to get to leaf. It may be more precise to control leaf temperature, because then you're right there at the level of the leaf. You decide which one you want to do. It's a trade-off of time versus precision, and that's something that each individual researcher kind of has to figure out what they want to do. The next thing to keep in mind is that the LI-6400 XT sensor head has some Peltier coolers. They're little thermoelectric coolers on the side of the sensor head that are used to raise and lower the temperature of the instrument block. They're just little ceramic elements with electric circuits inside. It's kind of like the radiator on your car. If you send the current flow in one direction, you heat the element. If you send the current flow in another direction, you cool the element. And that heating or cooling is transferred to the block and therefore to the air inside of your leaf chamber. You can tell whether the coolers are on by looking at the fans on the side of the sensor head. If they're turning, the coolers are turned on. If you've told them to turn and they're not, you may have a problem. Check your troubleshooting guide in the manual. The other thing to keep in mind is that these coolers have 6 degrees from ambient, plus or minus 6 degrees Celsius. If the instrument is in the sun and you have some radiative forcing, it'll be much easier to heat up and cool down. So you may get 8 degrees plus and maybe 3 minus, but that's something you'll have to figure out for yourself. If you can't obtain the changes in temperatures that you want with the Peltier coolers, you can also change environments by going into a warmer or a colder room. It's not necessary to go to Antarctica and talk to a penguin, but you can go to a warmer or colder room.
Thanks, Elizabeth. Before Tanvir takes his place, I do have a question from the audience, and that is, can I put just the sensor head in a growth cabinet to change the temperature?
Oh, that's a good one. And the answer is no, it's not really a good idea to put just the sensor head in the growth cabinet. What you want is to have the entire instrument at one temperature. If you have a large temperature change from the console to the sensor head, you'll have air at one temperature in the console coming through the tubing, and it'll hit the air at a different temperature in the sensor head. And that can cause some confusion. It can also cause condensation in your optical path and other things that will really slow down your measurements, if not halt them entirely. But that's a good question, because there are a lot of people who do try to use growth cabinets. It's important to make sure that everything from the sensor head to the console to the cable bundles is at the same temperature if you possibly can. Possibly in an Antarctic temperature, but possibly not. And it looks like Tanveer is about ready to discuss what happens if you can't use inherent controls, if they aren't enough. So I'll go ahead and hand it over to Tanveer for a little while.
Thank you. Those were some very good questions. Now let's move on to what if the inherent temperature control range is not enough. Really, the 6400 is designed mainly just to maintain ambient temperature and a little bit of variation from that. If you want an extended temperature range, then we do have an option. We call it the LI-6400, the 6400-88 expanded temperature kit. And this slide shows what this kit consists of. It consists of 2 water jackets, one on each side of the LI-6400 sensor head, and you can also see some of the tubing that connects the 2 jackets. This slide shows the 2 water jackets, one on each side. This is the front view of the sensor head. In this case, there is no tubing attached between the 2 water jackets, but when you use it, the 2 water jackets are all continuously attached so that water flows from one jacket to the other. The water can be circulated. You can use warm or cool water to take the whole sensor, the block, outside the range that's possible with just the thermoelectric coolers. Here we see some of the capabilities of the water jacket kit. With no water circulating in the installed jackets, the temperature control range is essentially unchanged from the default 6400 system, which doesn't have the jackets normally installed. So in this case, the range is the room temperature was 23 degrees Celsius, and we have a variation between 18 to 34 degrees Celsius. With the water of either 0 degrees Celsius or 43 degrees Celsius circulating through the jacket, the leaf chamber air temperature could be varied from less than 10 degrees Celsius to over 40 degrees Celsius, so a 30-degree range of temperature manipulation. Note the limit imposed by the dew point of the ambient or chamber air. If the temperature of the chamber is cooled below the dew point temperature of the chamber air, then condensation will take place somewhere, and it will become impossible to measure stomatal conductances and CI. That's because the evaporation from the condensed places will look like evaporation from the leaf. And not to mention other such problems such as condensation, formation on the gas analyzer optics. So all kinds of problems will happen.
Thanks, Tanveer. I don't have any questions from the audience right now, but thank you for submitting them along the way. We'll take the rest of your questions at the end of the seminar. Elizabeth?
Thanks for discussing the expanded temperature control kit, Tan. Sounds like that's going to be a really good option for a lot of people who need a little bit of extra temperature control. And for the people who need a little bit of extra humidity control, we do have the LI-610, which is a portable dew point generator. It can provide a precisely controlled stream of saturated air, and you can match the flow rate to the LI-6400 XT's flow rate, and you can control it via the LI-6400 XT using a little bitty program on the 6400. We have a little hook, software hook that tells it how to do that. On the other hand, there are a couple of cons to using this instrumentation. I mean, for one, it's another piece of equipment that you've got to use, and you've got to make room for it wherever you're doing your measurements, and you've got to make sure everything's fine. For another, if you have both the 610 and the LI-6400 on the same AC circuit, you can end up with a little bit of a ground loop, which can cause noise in both of them, and you want to avoid that. So you would want to make sure that one was on battery and one was on AC power if you did. The other thing is you'll have to make some chemical column changes. You'll have to put your chemical columns, for example, your soda lime, before the 610, not after, because otherwise the flow rates change and you end up adding CO2 and things like that. So you do have to make some chemical column changes.
Elizabeth, can we stop for a moment for a question?
Absolutely.
I have a question about using a bubbler.
Yeah, that's very popular, but we don't really recommend it. The thing about a bubbler is it does humidify the air. However, since you do have liquid water in there, and most people do a bubbler with liquid water, and then you've got an air hose in there. Well, if your air hose goes into that liquid water, you can end up sucking water into your LI-6400 console. And not surprisingly, things that are meant to deal with air really don't like dealing with water. That can end up a slightly expensive trip back to Nebraska in some cases. At the very least, you'll be replacing tubing. At the worst, you'll be replacing pumps and things like that. So we don't recommend using a bubbler. Use the 610, or you moisten your soda lime, or change your environmental conditions, but we don't recommend using a bubbler.
Thanks, Elizabeth. Let's take some final questions. The first question I have is, how often should I set water vapor 0 of the LI-6400 gas analyzer?
That's a great question. Thank you for asking. Well, unlike CO2, water vapor is a more clingy substance. It adsorbs and desorbs on surfaces very slowly. If you put the desiccant control on full scrub, you will notice that the gas analyzer water vapor signal goes down quite slowly in comparison to when setting the CO2 0, for example. This is because it takes time to drive the water molecules off the surfaces of internal walls and chambers and tubing. So expect to take a minimum of 20 to 30 minutes to get a really good dry down of the sample chamber of the LI-6400, and then set your ergo 0. The best philosophy in my mind is really to take plenty of time when setting the gas analyzer 0, water vapor 0. Otherwise, it's better to leave it alone and just do nothing. In other words, either do a really good job or don't do anything. If you are sure that no one has been fiddling about with your LI-6400, then you certainly don't need to set the water vapor 0 every day. The most important thing to ensure good measurements is to match the gas analyzers before taking the first readings, and whenever either the CO2 or the H2O has changed significantly. And don't worry too much about zeroing the erga for water vapor.
Thanks, Tanveer. The next question is a little long, but I think we'll take it anyway because it's a good one. When I use the fluorometer chamber for gas exchange measurements on narrow drought-stressed leaves of peach trees, I get negative CI values. But when I use the 2 by 3 centimeter red-blue LED light source chamber, everything is okay. Can you explain why I have problems with the fluorometer chamber, but not with the 6400 O2B red-blue LED light source chamber?
Okay, let me answer that one. Another really good question and very appropriate for this subject. The answer to this question is really closely related to the previous answer to the question previously given about setting the 0 calibration for the water vapor. It really comes back to the clingy nature of the water vapor and its slow absorption and desorption from internal chamber wall surfaces. The 6400-40 leaf chamber fluorometer has a leaf area aperture of only 2 square centimeters, but has a relatively large dome-shaped interior with a large area. The water vapor transferred from a small amount of drought-stressed leaf material is buffered on the internal walls of the fluorometer chamber. With drought-stressed leaves, the evaporation rate of water can be similar to the adsorption of water on the dry interior walls of the fluorometer chamber. This can easily lead to sample chamber water vapor mole fraction being smaller than the reference reading of the gas analyzer. So, in other words, because of the adsorption, the sample chamber water vapor reading can be lower than the reference cell reading, which has a much smaller volume and a smaller internal wall area. But the sample chamber really is the one that has the leaf in it, and it's supposed to be higher than the reference chamber. So this inconsistency is the problem and is the most frequent reason for getting bad or negative CI values. But with the 2x3 centimeter, 6 square centimeter 6400 O2B LED light source chamber, the leaf area is larger. It's so much larger, and the internal wall area is significantly smaller than with the fluorometer chamber. So the water vapor reference and sample delta measurement is much more robust and reliable for small stressed out leaves when using the 6 square centimeter red-blue LED light source chamber. So the main lesson is to maximize the amount of leaf material inserted into the sample chamber, and don't use the smaller aperture fluorometer chamber just because it's a little bit more convenient to estimate the leaf area when using the 2x3 red-blue light source chamber would really be better. A very good question and well worth the extra time it took to answer, as it really covers aspects of humidity control that we didn't adequately address during the presentation. Thank you very much for that question.
I'm going to go ahead and wrap it up. If you have any questions that you haven't had answered already, please feel free to ask them now. We might not be able to answer the extremely complex ones, but we will definitely make sure your question is answered.
Thank you, everyone, for your questions. I'd like to remind our audience that this presentation will be available on our website in the coming days.